All right, I think we can get started. There are like over 40 people right now. So, hello and welcome to ESSEC Seminar Series. This is John, the seminar coordinator, and together with me is Ms. Kathy Medley. She is our communication specialist. Kathy and I will be today's moderator. Just so you know that this seminar is being recorded and will be later published on our YouTube channel. Please be free to ask questions. You can do so by sending us message through chat, or you can raise your virtual hands and we will unmute you. And today we are excited to have our distinguished speaker, Professor Sorooshian. So Professor Sorooshian is the director of the Center for Hydrometeorology and Remote Sensing, and he is also the distinguished professor of the Civil and Environmental Engineering and Earth System Science departments at UC Urban. He is currently chair on Rosenberg International Forum on Water Policy, University of California, Division of Agriculture and Natural Resources. And he is a member of the U.S. National Academy of Engineering, the International Academy of Astrologics, and Fellow of TWAS. Professor Sorooshian's research area is hydrometeorology, water resource systems, climate studies, and application of remote sensing to earth science problems, with special focus on the hydrological cycle and water resources issues of arid and semi-arid zones. Let's welcome the speaker, and Professor, please proceed.
Well, thank you so much, John. I appreciate that. Good afternoon, colleagues. I guess I've known many of the scientists and friends and colleagues at ESSEC, and it's a pleasure for me to have been invited to give this talk. And I will actually now share the screen and move on to my presentation. Hopefully everything will work, and I will get feedback if that's not the case. I hope the voice is okay, John.
It works fine.
All right, fantastic. All right, well, anyhow, let me start, and let me just reduce these windows so I can see. How do I? Okay, I took care of it. So the topic I chose was the hydroclimate and modeling and application to water resources planning. What are the expectations? What we have promised and are promising still, and what are the realities? And I am, as was mentioned by John, let me just also get my pointer option. Okay, I got it. I'm working. So here I am at the University of California, Irvine. I was at the University of Arizona for 20 years and moved here in 2003. UC Irvine is one of the 10 campuses of the University of California system. And we're about 33,000 students at the present time. And I usually like to acknowledge some of the people who have worked with me over the years and some of the more recent students who have been in our group. And I, of course, give quite a bit of credit to them for some of the work that we have been able to do through our center. I don't know if Hugo is there or any of the other colleagues who are familiar with GVAX and WCRP. My involvement in hydroclimate actually started when I became involved with the GVAX program more through the GCP over the United States. But later on, I had the pleasure of chairing the GVAX Science Steering Group for 10 years. And the whole concept of GVAX was to close the water balance at the continental scales and beyond. And it involved process studies, it involved data assimilation, model coupling, and that is an activity of the WCRP that is still ongoing. And one of the things is that the science that you develop, you really hope that it will have an implication in application, and therefore there has to be an interface with engineering. So you develop models, you develop databases, and tools and technologies that hopefully will have an implication on water resources and hydraulic engineering. The big questions we always get, and I'm sure a lot of you do, how will climate change affect precipitation variability and water availability? Because for hydrology, it's the precipitation that really matters as a driving force on the either watershed scale or any scale. And without rain, you have droughts, and with too much of it, you have other problems. And the big question is, can we predict the future changes which are responsive to the user needs, not just for academic purposes of publishing papers, but what is the implication of those? So two primary water resources and hydrologic challenges have faced us, whether we are in the engineering or the science side of it. The first is, of course, hydrologic hazards, floods and droughts, and we've seen more incidents of these in the past several decades. And the other one is water supply requirements, both in terms of the quantity of water required and the quality. And we will not get into the quality of it, but a little bit on the quantity side of it. So with that in mind, then what are some stresses on the water resources and also related ecosystems, because we have to worry about the environment and meeting the requirements of the environmental systems. First is the population impact. It's much more predictable. Demographers are pretty good with their models and projections of how the population of different regions or the whole world grows. The second one is, in the context of this talk, is the climate impact. And I'm glad to see that again with the new administration, higher priority is being put on climate and its consequences. So, but it's less predictable, and we will get into that in a few minutes. If you look at the world population, all these red circles represent mega cities or large cities with populations depending on their size. In different regions of the world, as you see, Asia, of course, is dominated by mostly bigger cities. A couple of things to take from this picture. Of course, the global population projection is to reach about 8 billion plus by 2025. And then also it's important to note that before 1970, or roughly about then, only 37% of the total world population lived in urban areas. Since then, and after 2010, it's been just a lot of migration to larger cities, and people are moving towards cities and less in the rural areas. Also, another take-home message from this is that it took about 200,000 years of human history for the world's population to reach 1 billion, and only 200 years more to reach 7 billion, which we surpassed a couple of years ago. So it really puts a lot of demand on water, which is essential for life and everything else. So if you look at sort of the projections, or at least the estimates of how water is being used in different parts of the world, if you look at the US, we are roughly cut between both agriculture. The pie chart, the green part represents the agriculture, the blue part represents the industry, and the yellow part represents the essentially the domestic requirements. So to just see that we, of course, are split between majority of the use between agriculture and industry, but there are countries like China, India, Iran, where I was born, the dominant user of water is in the agricultural sector, and part of the problem is because of the efficiency. In the US, we've reached quite a bit of efficiency. If you look at the Western United States, which I happen to be used to be in Arizona, and now I'm in California, that as you see in the Western US, most of the water is consumed in the agricultural sector. Arizona is still about 85%, California about 83%, and we've reached quite a bit of efficiency in the US in terms of the utilization of water, particularly in the agricultural sector. So how we have come to address these needs and try to smoothen out the availability of water and handle extremes has been really mostly through engineering approaches. We control, we store, we pump and transfer water to where it's needed. And industrial revolution has really resulted in our ability to accomplish a lot of these things. And of course, some of them are good, some of them have had negative consequences, which are trying to be addressed. But it's not something new. Human ingenuity has been there for centennials. And if you look at this is an old dam in Kerman, Iran, maybe 500 to 700, 800 years old. That's near the city where I was born. And believe it or not, it was constructed by then by really basic things, stones. And as far as the concrete, they didn't have any concrete. It was mostly gypsum and eggshells that were mixed, and they're pretty strong in terms of bonding these things together. And nowadays, of course, we pour concrete and build huge dams, such as the Glen Canyon Dam on the Colorado River. In the US, we have over 70,000 dams, but we haven't been building anything past 30 years. China is still on the building phase, and they've already reached over 90,000 dams and building more to meet their requirements. Well, if you have the water available, you've got to make sure it gets where it's needed. And again, human ingenuity has been there with us. Roman aqueducts were raised in order to take advantage of the gravity and send the water from point A to point B where it was needed. And when you go for a visit to these countries such as Rome, and you go to the city of Petra, you will see the carvings in the sandstone that took the water from where it was available into the main parts of the city of Petra. But nowadays, we build these giant aqueduct systems and transfer water where it's needed. This is the Central Arizona project, which water has to be lifted, pumped out of the Colorado River, and delivered to the bigger cities such as Phoenix and Tucson, Arizona. And ironically, this project some 40 years ago, 30 years ago, was pushed by the agricultural system people in Arizona. But once the water arrived and they saw that the water quality of it had the salt in it, they decided not to use it. And they decided to go with their own groundwater and made it a big problem for the two main cities, which now they are treating it and recharging the aquifer systems at a huge cost. So part of the engineering is really how do you manage a variability that we have. In California, much of the rain falls in the northern part of the state, 75% of it, and in the southern part of the state is where the demand is, coming from the agricultural Central Valley to Imperial Valley and the larger cities of Los Angeles and greater Los Angeles, San Diego. We're all now connected together. So for that reason, all these lines that you see are the big aqueduct systems and canals that have been built to transfer the water from where it's plenty to where it's needed. And one of the biggest use of electricity in California happens to be the water sector, because we have to lift the water in many places to deliver it to Southern California when it's needed. Then the other part, of course, a little perspective on history, is the groundwater Again, human ingenuity dating back a couple of thousand years ago, they realized that if there was a spring someplace, there must be a source of that water, and they learned how to build canals, which are drilling wells vertically and hitting the main aquifer system. It was known as the mother well, and every 20, 30 meters, they dug other wells and horizontally connected these and took advantage of the gravity. This was something done by the Persians and the Persian Empire extending all the way to Egypt at that time and India. You see a lot of these canals, but they're no longer functioning. Why? Because with the advent of drilling bits and ability to have drilling rigs to go, and within days you can dig a big well to hundreds of meters and start pumping water out. Many regions, of course, have suffered substantial and unsustainable groundwater depletion, and in the coastal areas, sadly, that has resulted in saltwater intrusion. And in California, we now pump a lot of fresh water to try to block the salt water from intruding inland. So these are problems that water resources folks have to deal with in different parts of the world, but groundwater has become a increasingly worrisome problem for most. So what are the expectations? Expectations are for us as scientists to provide useful, relevant, and reliable information for not only operational, but for planning and design of water resources systems. So in order to do that, what do we have in our toolbox to try to develop the relevant information? Number one, we take advantage of observations. And number two, of course, these days with mathematical models, you try to use them and see if there's any aspect of it that could potentially be of value to people who have to make decisions for various water resources applications. So observations, we have in situ, we have remote sensing, we have proxy information, and models from a hydrologic point of view. A lot of it has been data-driven through statistical hydrology and stochastic methods. And in fact, if I recall, Richard McCune, one of the faculty in civil engineering at the University of Maryland, where you guys are associated with, located, was one of the people who did a lot of work in this field. Then we have physically based hydrometeorological and hydroclimate models. So in terms of the observations, we have in situ, we have remote sensing, we have proxy data. And so if I was to draw a line here, say present, what do we have? We have in the past, not more than maybe several hundred years of instrumental observations. And, you know, I don't want to preach to the choir. You folks there know a lot about, let's say, precipitation measurement, gauges, radar, etc. But realities are that the instrumental records, such as stream gauging, in the lifespan of our planet are very limited, for only several hundred years at best. But then in the past, we also have proxy records, and isotope hydrology has worked quite a bit to help us in that regard. And tree rings have been used to kind of see what the patterns of precipitation in the past have been. And only 50, 60 years, maybe we have remote sensing, and they have become a great player. And again, you folks are probably among the main contributors to this area. And then we rely on models for future projections. So speaking of proxy records, this work was done by some colleagues who are isotope hydroclimatologists. Overpeck was at the University of Arizona, now Dean at the University of Michigan. They used dry depositions from some dried up lakes in central US, Nebraska, And anything below this line is periods in a 2,000-year period that were below average precipitation. Anything above it, which is the greener bars, and bluer bars represent above average of the 2,000 in terms of amount of precipitation. So what you can see from these isotope analysis that has been done, there have been periods of hundreds of years of mega droughts. And if you want, and a lot of us in the US have familiarity with the 1930s Dust Bowl. So the Dust Bowl here pales as compared to some of the big mega droughts that have been experienced in the past. The good news is from 1900 to the present time, for most part, we have been experiencing wetter than average period of record, and that's what has saved the Western United States pretty much. So if I go now to use of some of the observational records in hydrology, and first I talk about stochastic methods, and those have been crucial in study of extremes, particularly for water resources planning. And stochastic hydrology has been the foundation of it. And when I was a student, I had to take courses and prepare some flood frequency analysis as a part of the homework. Unfortunately, these days, I don't think that many universities are teaching these things, which is unfortunate, but anyhow, but still, it's still the backbone of a lot of engineering consulting companies and government agencies, and to try to come up with let's say the definition of the 200-year flood, 100-year flood, 25-year flood, and used for design purposes. So what is traditional statistical hydrologic methods all about? It's, let's say I have a watershed, I have some recorded data at a gauging station, and my advisor back 40 years ago or so would assign us to go and get it from USGS books for a given river basin. So you would have the annual record of the floods, and then what you do is you either had to do a partial duration series or an annual series, and to look at the extremes. So if this is a partial duration series, you would draw a line. Anything above it, you would fit a probability distribution through that data, okay, which was usually a skewed distribution, and log Pearson type 3 has been adopted by most places in the world as a way to do statistical hydrology. So based on that limited record of data, you would fit a distribution to your data and then use that distribution, and assuming that history would repeat itself, and you would assume stationarity, you would use the properties of that probability distribution and generate future scenarios of stream flow. And so that's what has been used a lot for even dam building and other activities in water resources. And as I said, the assumption was that if I had a statistical distribution fit to my data of this, let's say in the middle of Rio Grande Basin, then if I would assume that the history is going to repeat itself, I use the properties of that in order to look at the extremes and see how I would use that information for my planning. Well, we know that, of course, climate has changed, and you know, these techniques may have problems, and there have been a famous paper written that stationarity is dead by I think Chris Milley and colleagues, that has taken a lot of attention. It's not that they discovered anything, it's just that we make the assumption of stationarity for convenience, as we do in rainfall runoff modeling. We assume watersheds are linear, which we know they're not linear. So if I look at this and you get a semi-log paper, you fit the data, and you come up with the semi-log return period flood frequency. If you fit a straight curve through that gives you an idea that if you wanted to look at a 100-year flow for this hypothetical river that I had, then you hit the line, you go there and you read the magnitude, you say, well, this is the amount that, according to the statistics of the region, shows a 100-year flood. The issue with climate change and variability that we are seeing that even if the mean is the same, we see more variability, either higher variability for some regions or lower variability. So the original statistical hydrology that I had is no longer really adequate, perhaps, to capture these variabilities. So what was a 100-year storm of 4,000 CFS, and now within more variability is going to happen much more frequently, and as such, that all the designs that were done based on that are maybe less relevant today. The same goes in the other direction, maybe in a positive way for planning purposes, that if a region becomes less variable, then maybe the 100-year storm that we had before is now going to reoccur or comes back every 500-600 years. So that's really the big problem with how we see impacts. The other aspect of statistical hydrology that is also important is that if you urbanize an area, you certainly change the flow regime and the input from the same storm over the area, because you have more pervious areas, roofs, etc., and therefore the adequacy of what you had based on historical data is no longer good, because you may have more picket hydrographs, and as a result, these are the type of consequences that we have. We are really seeing a lot more damage done to the infrastructure, and this has become a big problem for highway or the departments of transportation and other components of our field. So let me now go shift a little bit to model projections. That was enough on the statistical stuff, which are models. But if I go to model projections, the reality is, what is the current state of model projections that are relevant and useful for water resources planning? Again, you guys are probably best in this field, but we really could break it up into three. We have short-range forecasting in hydrology and water resources that are important, mid-range forecasting, and long-range forecasting. The short range is in the area of flash floods and floods that are hours to days. Mid-range would be maybe a seasonal forecast of up to 3 months, and long range for large planning of structures is really the work that or information that we get usually from climate models. So let me go over these briefly. John mentioned that people associate me with hydrologic modeling. I had removed this, but luckily the conversation before the talk allowed me to put a few things and talk about the short-range forecasting, which is at the weather scale. It's floods and river flow forecasting. Much of it is based on the hydrologic models that the Weather Service and others have developed, or scientists at different institutions. And there are three elements of the hydrologic model. That one is the model that you select or develop. One is the data that's required for the model to run and be tested. And models are usually parametric. So you have to worry about how you parameterize or calibrate the model. And my work originally for my dissertation was on parameter estimation using maximum likelihood estimation. If you are fortunate and these three pieces come together, you have a perfect model of the watershed and useful for forecasting, which unfortunately is never the case. Part of it is the hydrologic system is a complex one, it's highly nonlinear. But evolution of hydrology started from what we call API model, antecedent precipitation index models, back in the 30s, and very basic pragmatic engineering approach to do some river flow forecasting. I won't get into the details of it. With the advent of digital computers and the work by Ray Lindsley at Stanford University using an early version of IBM 360, with his student Crawford, they developed the first lumped hydrologic model known as a conceptual rainfall runoff model. Since then, we've had both capabilities of models and the ability to look at the heterogeneities and come up with more distributed model. In the past several decades, as we interface climate with hydrology, then we have distributed models such as VIC model that are used in the regional analysis of the climate system. So in terms of complexity, we went from lumped to distributed models, and as you go more distributed, obviously you need more information. And it goes from more simple approaches to more physically based and complex approaches. The bottom line is when it comes to hydrology, and I can't go into too much detail, I don't have time, people in the academia developed all these fancy distributed models and complained to the Weather Service, and it was known as sort of the Sacramento model because it was developed at the Sacramento office by Bernash at that time, that, you know, you guys don't really transfer more advanced methods and come up with more distributed models to capture the precipitation conversion into runoff. So under pressure, I guess they initiated what was known as the Distributed Model Intercomparison Project, DMIP. It was 2 studies, 1 and 2. I just give an example of the first one. And they compared a lot of these models, and the report, the paper is there, and there was one back in 2000, maybe 9 or so, as a follow-on, and by Mike Smith at the National Weather Service office, Silver Spring, not too far from you. And the bottom line was no major difference between the performance of lumped and distributed models, if, of course, the lump models are well calibrated. And so I will not dwell on this anymore, but at the present time, we know there's a lot of activity at NCAR and others, and the Water Center in Alabama, trying to develop the WRF Hydro and bring a lot of these features of distributed components. But for some of us, like a lot in your shop, working on precipitation, we know that the limiting factor is going to be how accurate are the resolution of the precipitation estimation, because it has to feed into these models. So let me go now on terms of the mid-range and long-range, because that's been the subject of a lot of papers that appear in the literature, my God, from regional analysis, and some of them are, of course, a lot of news making, like one region is going to go completely dry, etc. But this concept has been really take a grid of the climate model and downscale it, bring it down to a watershed. So the downscaling happens. The methodology that has been used has been mostly to create the ensemble approach, take a bunch of models and initialize them and run each of these models separately based on the initialization from a climate model, and generate different sequence of precipitation and then merge them together and create a ensemble of those precipitation scenarios from different models. Then take those outputs and feed them through a hydrologic model and generate further sequences that theoretically speaking, and in papers argued that they can be very useful for planning purposes. But the bottom line is, how good are the outputs of the models that we are going to use for these activities or purposes? So what do climate models tell us about the future? I think this is really the most important question that we all have to ask. Let's look at the mid-range. And I'm sure some of you or most of you are familiar with different centers, even NCEP, producing seasonal forecasts. I usually use the IRI, International Research Institute at Columbia University, and they have come up with various products, including one that is 3-month multi-model probabilistic precipitation forecast based on a 24 models that they use. And I showed this one as an example. And I'm not diminishing the importance of the work they do. They're just doing an incredible job and making improvements, such as NCEP and others. But the realities is when you talk about their applications for water resources planning, etc., the question is, are they really reach the reliability that we could trust them? So anything on these maps that is of these warmer colors probabilistically indicate that those regions in the next 3 months, and this was issued December 2018, for January, February, March of 2019, and the cooler colors represent those areas will see an increase in precipitation. I highlighted 2 of these. That December 2018 forecasted that, let's say, western coast of United States and California probabilistically showed some slight degree of decrease in precipitation. And I was also monitoring Iran, and believe it, both of those in the month of January and February and March received a tremendous amount of precipitation. And in fact, they were in both regions were record breaking. So again, models have improved, but sometimes their predictions are not necessarily that accurate. And I think IRI has been careful about this. It's a probabilistic forecast, and you have to take it with a grain of salt. I mean, this is probability. Well, what do they show for the future? This is last month, February 2021, for March, April, and May, and we shall see. Unfortunately, it doesn't have too much of a good news for us in the Western United States, and we shall wait and see. Now we go to long-range forecasting, and again, I had the pleasure of having then a postdoc from Beijing Normal University. Is now a full professor at Beijing Normal, and he spent some time with us, and I still collaborate with him. And we've been looking at these to see how effective have the CMIP models, both 5 and 6, have been in projections of precipitation. They do great with temperature, but precipitation. If I focus on the Western United States, and particularly California and Arizona and others, and this is the scenario 8.5, which is the high end of CO2 emission, and I have it for lower one, but I just have this to show you that you will see this is for the CMIP 5, that 4 different models, not all 20 or so, but only showing 4, the French, the Australian, the US, and the UK. You see they're quite a bit different in their opinion of what is going to happen in West California for the next 100 or what's left of it, 80 years. So the Australian model, for instance, projects we're going to get wetter. The US projects that we're going to get drier, and you will see that they are quite a bit. So the key question was how we improved. If you look at, for instance, the latest ones out of the CMIP 6, when it was available, I prepared this for an AGU talk a number of years. Unfortunately, we still see that the models from different countries are still having different opinions. 2 of them show that the Western US is going to get dry, and the Canadian model still shows that we're going to get more rainfall and precipitation. So to kind of summarize what I wanted to say up to here, the take-home message is presently the accuracy of hydroclimate model predictions falls short of meeting the requirements of water resources planning, and they're hardly used for operational purposes, and it's unwise to push their use while highly uncertain. So what's left for us is the old engineering approach of building resiliency, having conjunctive use in mind. For instance, the city of Irvine and the Orange County in general, when you talk to water planners, they say they don't worry about droughts in California anymore because they already have sufficient amount of water from wastewater treatment that they recharge to the aquifer. So they use that conjunctively in order to make sure that they have a sustainable situation no matter how long a drought lasts. So that's really the message. So promises. We really always have to improve things. We need better models. We need better observation analysis tools. And we have to be more realistic about what we promise, not overpromise. Well, here I talk a little bit about precipitation. I'm again preaching to the choir. You guys are all experts in this stuff. But a key requirement is precipitation for driving hydrology and hydroclimate models. And I'm planning for statistical approach aspects. This picture I took from my house in Tucson some years ago during the monsoon season. It's a thunderstorm that hit the foothills of Catalinas. 45 minutes of rain devastated a bunch of multi-million-dollar houses. And of course, the gauge is at the airport somewhere in that side and showed zero rainfall for that day. So at the end of the day, it is an important challenge. We need to have adequate, high resolution, both in time and space, in order to not only use for model inputs, but calibration testing and dealing with extremes. So we have rain gauges, we have weather radars, we have satellites, and which one to trust. I guess each one has its strengths and weaknesses. The problem with gauges, which would be the best, because you're really measuring what falls on the ground, is that we don't have enough of them, and it's impractical to have them. If you look at China, for instance, the monsoon region has 2 gauges per 10,000 kilometers on the average. The drier regions of China have 1 gauge per 25,000 kilometers square. In the Western United States, on the average, the official gauges cover about 1 gauge per 600 kilometers square, and it's mostly in the urban areas. The mountainous areas that do get the rain probably are less covered. There has been a lot of work done, and we have a Doppler radar system deployed over the United States. This is from the Tucson Doppler radar. And when I was there, we did some work with Efrat Marine, published this paper. And during the monsoon season, you get a lot of rain. And there is a well-known watershed run by the Agricultural Research Service, known as the Walnut Gulch watershed, which is closest that you can come to reality. It has a gauge almost every square kilometer and covers the entire basin, and incredible source of information. Radar is about 50, 60 kilometers away from there. And this is the storm on August 11, 2000, that was picked by this radar, which shows quite a substantial amount of rain, but then what fell in the ground was quite different, almost 70% overestimation. And that's explainable because during the summer in Southern California, Arizona, you have temperatures as high as 110, 115 degrees. So what you see in that convective cell up there, as it falls down, it evaporates back to the atmosphere, never reaches the ground. So radars have their problems, aside from the fact that in the mountainous regions, they have limitations. So for next few seconds, I'll talk a little bit about the satellite observations. Again, you guys are probably at ESIC and NASA and NOAA in Maryland, perhaps some of the most important work you do. But for our little part as an academic institution, I had the pleasure of working with some students since the 1991, 92, and we developed, based on neural networks, what is known as the precipitation estimation from remotely sensed information using artificial neural network, Persian system. And I recall I presented the concept, because for hydrology, you need high resolution. And at that time, the best satellite product was 22.5 degree monthly data. And I presented this at the working group of precipitation in Frascati, Italy. And when I gave the concept that we are going to push more towards using neural network methods to get high resolution precipitation, one distinguished colleague said, if you think you can get it with a black box, you're crazy. Well, the bottom line is that I am probably crazy. There is no question about that. But I never gave up, and we worked on it. And I think a lot of people are now appreciating that machine learning tools have become an essential tool in our toolbox to try to do. The physics is still important, but data has a lot of information. So Colin Shu was a PhD student at that time. Now he's a professor here. He developed the neural network approach known as the Persian. We use mostly IR because we need high resolution in time and space for hydrologic applications. And of course, the folks there that are working on the GPM and the iMerge are also developing the same kind of things. And I'm happy to say that till now, a part of the iMerge algorithm has been based on the work of Colin and Hong Yang, which is the CCS algorithm. So at the present time, we have really most of our data served on our website, CHRS RainSphere, which is our climate data, which we developed for NOAA, and CHRS iRain, which is our real-time kind of weather scale. And then much of the data is served through the data portal. You may consider this to be a little promotional advertisement, but people use whatever they think it suits them for their application. We monitor who uses our data. And thanks to Fu, who developed this page, there are about people from almost 211 countries that have visited our site or are doing that. The amount of download of the data from our own site is this much. And of course, for the climate scale, it's the NOAA site that serves the data. And much of our data is put on our data portal. And it has a tutorial that explains how you can essentially customize the data you need and download it or receive it. Our iRain, which is our real-time data, I won't get into much detail of it, but that website also has a tutorial and shows how you can carve out the data that you like. I downloaded this from last week when there was a major storm passing through, Kentucky, Tennessee, etc. And we have incorporated for the US also the radar information, and this was the comparison between what we did and the radar over this area, which looks good, but not always the case. But those are the challenges that we have to face. RainSphere is the one that represents our global satellite data. And that data is also actually released through the NOAA and NCDC. And now it has about 37 years of data, and hopefully will continue to grow from 83 to the present time. And Fu was the one who put this information together. And the work on the Persian Climate Data Record, CDR, is an algorithm that was developed by Hamed Ashuri, who now works for Facebook. Yeah, unfortunately, didn't stay in the field. They pay better, I assume. The data period is 83 to almost present, 60 south, 60 north, and spatial resolution is a quarter. And now we are moving towards a data product that is final resolution 4 kilometers. And the paper was published in BAMS, and it's well cited. And I'm happy to say that both Fu and Hamed in 2019 received the WCRP GCOS International Data Prize for the work they've done in this, because it's used quite a bit through UNESCO and other agencies. So what does this data set bring? If I'm focusing on the, let's say, Sierras in California, I can look at all the data daily up to the present time. If I take a year, I can look at it by month. If I take a month, I can look at it by days. And these are the averages over the 37-year plus that we have the data. If you go to the website, you can look at the data based on looking at the state, at the country, at the watershed, and get the historical records of it. And from there, you can look at actually a month and look at by day. Another part of it, we look at the rain trends, and it's available on that website, which gives you the precipitation history over the globe. Warmer colors represent areas that have seen a decline in precipitation. If they're hashed, that means that they're not statistically significant, but there is a downward trend. The bluer regions show areas that have seen increases in precipitation. And then you can go from, say, the country, look at by states or by watersheds. And here are examples for 3 countries: US, Iran, and China. And you can actually look at this data. And unfortunately, in the United States, the only place that we see statistically significant decrease in amount of precipitation has been over the Colorado River Basin, which is a crucial one, not only to serve California, all its thirst for water, but also provide water for Arizona and other places. And Cadillac Desert and others are the books or movies that sort of tell the disputes in this region over water. And if you look at it, it is actually statistically significant decrease that we see, but not for the rest of the US. So I'm getting close to the end of my talk. Many regional evaluations have taken place in the literature, over the US, over Iran, over many countries, over Africa. And as is the nature of these papers, they compare them with Seymour, with others. A lot of the studies are really apple and orange comparisons. I think this is the thirst of these publishing groups that accept these papers. A lot of them, of course, say we walk on water, and the other one said you guys are terrible. The same goes for other products. But the bottom line is these are the lowest hanging fruits. And sadly, you see, for instance, comparisons done over North Africa, over Tunisia with 4 rain gauges, and compared satellite products with the resolutions of even 25 kilometers, which doesn't make sense. But anyhow, somehow they pass through the review process and they're published. So what is the value of such a data set, particularly this climate scale one? People have used it in order to look at the efficacy of climate models because they run in the retrospective way as well. These are 5 models, and if you compare it for the period of 83 to 2005, for instance, in this study, you can say that maybe a few of these models seem to capture the precipitation pattern over these areas as compared to these high resolution data. And then maybe out of 30 or 25 models, you can cherry pick the ones that perhaps did better on a historical basis. And then maybe you can create an ensemble of those subset of models for projections of the future. The other aspect of it has been we've used the data, and Mohammed Umbadi and Puya were the PhD students who did the work for flood frequency analysis. The question is, if you don't have the gauge information and it's sparse, is there a way that perhaps satellite information could show potential use for flood frequency analysis? And indeed, that's the upshot is yes, even though we are still short 35 years as compared to maybe 100 years of data you want. They looked at 20 river basins across the United States. They looked Persian CDR, and we adjusted, bias corrected it for elevation. And the bottom line was that it was consistent frequency estimates as compared to the NOAA Atlas 14. And in fact, the bias correction was important for elevation. And we are seeing that maybe this is one area that satellite information, whether generated from us or from your group and others, could have implications. Closing, despite advances to date, predicting the future hydroclimate variable will remain a major challenge. Nature is complex, and observing and modeling its non-stationary behavior is very challenging. So my recommendation always is have some will to doubt the credibility of information generated by models. The same goes for remote sensing information, and we have to always try to make those improvements. And that's why it's so important to have long-term and sustained observation programs that are critical for not only model testing and verification, but also for use as input. At the meantime, again, I come to my engineering instincts that factoring in resiliency in water resources systems, design and planning is still the safest approach. And thank you so much for the invitation and listening to me.
Thank you, Dr. Sorooshian. Oh, we already have a question. Oh, there is a bad echo coming from your side. Oh.
From my side?
Wait, maybe this is so strange. I guess it's done now. I don't hear any echo. If anyone does hear echo, please send me something in the chat. Just if anyone has any questions now, they can raise their virtual hand or type it in the chat. We already have one of each. So I am going to unmute Ahmad Tavakoli. Ahmad, you are unmuted now.
Dr. Sorooshian, great to see you, and also thank you for the presentation.
Good to hear your voice.
So I have one question. So in the first slide, you mentioned that was a great slide to combine engineering and science, those circuits. And then at the end, it was about like the middle of your presentation. You mentioned that we cannot push to operationalize our system, our models, because of the uncertainty and the errors that we have in the predictions. From the being working for the government and also being in touch with the scientists and academy, right, we are getting lots of those requests from first responders that about like having a modeling framework. They are apparently there is a big lack of operational system to predict, for example, hurricane, which is happening like the last year, like we had 7 hurricanes in the US. One of them was just 1.2 billion cost. And to study compound flooding like hurricane that we had last year, we need to couple the models. We need to have some prediction system. That was the main purpose of probably National Weather Center in Tuscaloosa, Alabama. In the grand opening in 2015, when I was there, the first responder from Alabama State says that if you have something for me before the flood hit the land with the 30% accuracy, it's better than nothing, because we are talking about a matter of saving people and also reducing the cost. So what is your recommendation if you are not?
Ahmad, thank you so much. No, that's a good question you asked. Of course, that conclusion slide that I showed was related to the climate scale predictions, for long-term, if you're building a dam, let's say in Middle East or China, and you rely on outputs of some climate models, I showed that they can be just the opposite of each other. So some people's solution to that is you just merge, create an ensemble. So I removed it from example of NARCAP study over Western United States, which was a combination of 3 climate models with 3 regional climate models that was done out of NCAR, hasn't unfortunately been repeated. And it shows that 3 of the combinations show that Western United States, particularly California, was going to get drier at the regional and a smaller scale. And 3 of them showed that they were going to get wetter. So if you are a water resources manager for that scale of operation or planning, which one, it's almost like flipping a coin, right? So all I'm saying is that we have to be careful. We don't push. And, coming from a developing country myself, like yourself, from Iran, I always resent trying to say improve things by using models in Africa and others if we have not been able to fully trust them, because you see papers, they say this area is going to go completely dry and this area is going to get flooded out of the world. And yet their selection are based on models that show those scenarios, because so when you come to shorter time scales, absolutely. I mean, the models have proven to be effective and we should pursue it. And yes, a lot of people say even with a low probability, I prefer to have it. At the same time, I should tell you, when I was in Arizona, Salt River Project, one hurricane system was moving and they predicted it's going to hit the White Mountains of Arizona. People at the Salt River Project had to make a decision how much water to release from the Roosevelt Dam. 48 hours before that, the projection was it's going to come and dump about 4 inches of rain over that area. Well, they decided not to do anything because they were protected by the legal things of following operational rules that were established over the decades with statistical method, okay? And in this case, they made the right decision because 12 hours before that, the hurricane, it was Nora, Hurricane Nora, took the path right over the Colorado River and dropped little rain over the White Mountains. If they had released water, summer water supply for Phoenix would have been in a dismal situation. So, you know, it's a tough one. As I said, hydroclimate predictions, both in short term and long term, are a very challenging thing.
Right. Yeah, I agree. I think for the short term forecasting, as you said, probably we can rely more on the models.
Yes.
The longer we go for forecasting, we have more uncertainty, and that we need to be careful about making decisions based on the models.
Precisely. So you use a combination of things. As I said, if I talk to people in Orange County water districts, which I do often, they say, you know, it's great. You guys talk about these models and their predictions, etc. Well, thank you. And they're polite. They say thank you. But you say, how much of it you use? They say not much of it. Okay, that's it. They're very honest with you. They tell you.
Right. Great, thank you.
So we do have a text question from Sushil Unayar. They ask, which specific / primary parameter in the CMIP models causes the difference in future precipitation predictions?
I'm sorry, I didn't get it. What was the question?
Okay, let me ask it. Can you hear me right now? Can you hear me? No?
Maybe you repeat it one more time. Which parameters, what?
So they asked, which specific / primary parameter in the CMIP models causes the difference in future precipitation predictions?
Could, you know, I'm really terrible with acronyms. What is CMIP?
I am not sure. If Sushil, if you are here, could you raise your hand and then ask your question verbally? Hopefully that helps clears us up. I'll just
maybe one of the other members of the audience knows what is CMIP. Is that climate model something? I don't know. Okay, I'm sorry.
No, we can give them some time to answer. But we can move on. We have some other audience questions. So we have Unsang Cho. I'm going to unmute you now.
Yeah, can you hear me?
Of course I can, Mr. Cho.
Thank you, Soroosh. This is great. So, and just question about your precipitation data set. In warmer climate, I think is the snowfall, precipitation, and snowpack would be important for water resource management, is particularly in the west societies. Do you think the precipitation data provided, for example, is a Persian to present, so provide by the pose of this precipitation, rainfall bursts or snowfall, and do you think its accuracy as a snow hydrology perspective?
Okay, well, that's a good question. You know, of course, what our algorithm does looks at the amount of precipitation that you can expect from estimate of precipitation, and it's being looked up vertically from the top. Now, what's underneath, it determines whether you're going to get snow or not, particularly in the western US over the mountains. Our system is not able to make that distinction, okay? So you need now a combination of things, and there's a lot of work going on, especially with the iMerge, to try to look at distinguishing between snow and things. At some years ago, my thought was, we are pretty good, when any precipitation passes through Southern California, the weather people tell you that the snow line is going to be at 5,000 feet. And I've always said, and we wrote a proposal and they didn't fund it, that we can now combine synoptic hydrology or meteorology with remote sensing in order to say that at what elevation above there is snow that has fallen and what elevation is just liquid precipitation. There are these different ways to do it. I wish a lot of students would be directed to work on this kind of stuff as opposed to just do another comparison of various precipitation projects.
Okay, thank you.
You're welcome.
Okay, I'm going to unmute Nima Pavlevin. You are unmuted.
Hi, Soroosh. This is Nima Palavan. Thank you so much for the presentation. It was fantastic. I'm not a hydrologist, and I'm a remote sensing guy interested in water quality. I would like to hear your insights on the relationship between water quantity and quality, and hear your feedback on how we can marry these two communities to be able to address all the hazardous situation that occur in water resources, in particular from a quality perspective and HAB monitoring and all sorts of issues. Thank you.
Sure, Nima, great question, and probably my answer is not going to satisfy you because I really haven't seen much. There are remote sensing sensors, at least for the coastal regions and oceans, to try to look at the extent of algae growth, and but to the details, I don't know what are the spectral bands that actually can capture water quality issues in lakes and others. I mean, to me, the biggest problems with water quality, and you said you're a remote sensing person, but if you talk to people in the water resources field, at least in the United States, we've done a great job since the creation of EPA back in the 70s when rivers were in fire, Cuyahoga River in Cleveland, Ohio. They cleaned up everything. So relatively speaking, we are okay. We are doing well with the surface waters. The biggest problems are groundwater, okay? And I don't think any remote sensing at this point is capable of actually detecting that. If that was the case, that would be fantastic. I lived in Tucson, the paint paint industry that helped paint a lot of the airplanes for the Korean War or before that, polluted the groundwater aquifer, and South Tucson aquifer system became contaminated, and a lot of incidents of leukemia, especially in young people. So they found out a little late, and then now they're doing a lot of cleanup because that's one of the areas where it's a Superfund site to try to erase some of the impacts of those. So those are really more to do with a combination of maybe remote sensing to help understand the surface better and maybe detect where the sources of the problems are, and then combined with hydrogeology and other things, try to look at how to get at least reduce the impact of those.
Thank you.
It's a tough one. Yeah.
So we also have Sushil, who I'm going to unmute. They had the question with the acronym earlier. Sushil, you're
Okay,
muted.
sure.
Hi, Soroosh. Great talk. My question was, you showed, of course, the difference in precipitation in different climate models, and that was my question. My question was which specific parameter or parameters in the climate models produce that difference, to your knowledge? Do you have any guess?
You know, I am not, Sushil, good to hear your voice. I mean, I was talking about GWEX, my God, now it takes me back to some
Right.
historical times when we were all working together with Rick Lawford and others. Sushil, I'm not a climate modeler. You know, it's hard. I know that only when you talk to climate modeling centers, they say that aspect of, they all start from the same principles, but you know, some models have, I don't know, 50 layers of atmosphere, the other one's 120, et cetera, et cetera. I have no idea where they show these discrepancies in the precipitation estimation. And it seems not to be the case when it comes for the temperature estimates. I have no idea, but what we did, we looked at the observations because, you know, I can show you papers in science that suggested that the Western United States, the drying of the imminent drying of the Western United States, okay? And if you read the abstract, in the abstract, if these models are correct, okay? Now, we get a paper in science, but realities are, I got a call from some water district people, say, did you see this paper that was announced today that we're gonna get completely dried up? I went and looked at, luckily the reading the abstract was sufficient for me to tell them, did you see that? Because, you know, there is even lack of confidence in some of these models. It's a hard.
You make a good point, because in some areas I know for a fact that there are international programs investing resources in water management schemes, which are multi-million-dollar projects.
Absolutely.
Based on this type of analysis. Yeah, thank you.
Absolutely. Yeah, sure.
Thank you. We also have a text question. Let me just pull that up. So it's from Gianpaolo Balsamo. They ask, a few years ago, there was a debate on the value of high resolution, labeled hyper resolution, for hydro forecasting in absence of OBS constraints. Are there reasons to think we can make better use of high resolution modeling and satellite in situ plus AI now?
Well, we always have to be, was that Paulo? Was that the name?
Oh, no. Oh, yeah. Gianpaolo Balsamo. I might be mispronouncing.
Yeah, Gianpaolo. Yeah. Well, we always, as scientists, we have to be optimistic that we should look at and take these challenges. You know, the notions of hyper resolution in hydrologic modeling have been discussed for decades. Personally, I've always said, I don't care how hyper resolution a model you make. All right, and you can write the equations to do it as it's been done. But the bottom line is, for every little pixel in that resolution, you have to have accurate or reliable precipitation estimate to put through that, to go vertically down to the subsurface. Can you produce that? Based on our experience, and I'm sure a number of people at ESIC and you know, NASA, Hoffman's group and Adler's group, etc., they realize, I mean, we cannot go too far with the highest resolution precipitation we have. The higher the resolution in time and space, the more uncertainty associated with that data. So yeah, you can create anything. You can create a car with an engine that is just going to do magic for you. If you don't have the right gasoline for it, it won't take you much in terms of advancing you. This is the problem. But you know, people work on these things. I think these are areas of curiosity, but at the end, you have to understand, hydrologic processes are pretty complex. Nonlinear, maybe not as important in view of a lot of people, but the bottom line is they are very challenging.
Thank you. That is all the questions I have in my queue. If anyone has any last minute questions, they can chat me real quick or raise their hands, but we can give it a second.
Thank you all for listening to me. I appreciate the opportunity, and Sushil, was great to hear your voice after so many years. Bye-bye.
Oh, wait, maybe we have one more. No,
Okay, sure.
He said, never mind. It was just Gianpaolo saying thank you.
Okay.
Thank you, everybody, for attending. Thank you, Professor Sorooshian.
Thank you, Professor.
Thank you so much. Bye-bye.
Bye.
Bye-bye.
Bye.